Hello everyone. Many of you were not able to attend online classes due to various issues such as network connectivity, etc. You need not to worry about it. Let us recap the topics we discussed during online classes. The list of topics discussed are displayed on the slide. Negative of line integral of electric field between 2 points is equal to work done by electric field in moving a unit positive test charge between the 2 points in the electric field. The electric field at a point measures the force experienced by a unit positive test charge placed at that point. Therefore, work done by the electric field in moving a unit positive test charge in moving it from A to B in the electric field is equal to integration of E vector dot dl vector with the limits A to B. The electric field possesses one basic property, that the line integral of electric field between 2 points is independent of path followed between the 2 points. Hence, it is conservative in nature. A force is said to be conservative if work done by the force between 2 points is independent of the path followed. Further work done by a conservative force along a closed path is always zero. Conservative nature of electric field leads to the concept of electric potential, an electric parameter of great importance. We know that a liquid flows from a higher level to lower level. Heat also flows from a body at a higher temperature to a body at lower temperature. Similarly, positive charge also flows from higher potential to lower potential. Just a flow of liquid does not depend upon the quantity of liquid but depends only upon the level of liquid. In a similar way, the flow of charge does not depend upon the quantity of charge. Electric potential at a point in electric field is equal to the negative of the line integral of electric field between reference point, which is usually infinity, and that point. Hence, electric potential at a point in electric field is defined as the work done in moving, without any acceleration, a unit positive charge from a reference point, usually infinity, to that point against the electrostatic force, irrespective of the path followed. SI unit of electric potential is joule per coulomb, that is volt. There is a freedom in choosing the reference, a point where potential is zero. A convenient choice is to have electrostatic potential zero at infinity. Note that the actual value of potential is not physically significant, it is only the difference of potential that is significant. We can always add an arbitrary constant to potential at every point, since this will not change the potential difference. Electric potential difference between 2 points in electric field is equal to the negative of the line integral of electric field between the 2 points. Hence, electric potential difference between 2 points in electric field is defined as the work done in moving, without any acceleration, a unit positive charge from one point to another against the electrostatic force, irrespective of the path followed. Consider a point charge Q at the origin, as shown in the figure. For definiteness, take Q to be positive. We wish to determine the potential at any point B with position vector R vector from the origin. For that we must calculate the work done in bringing a unit positive test charge from infinity to the point B for Q greater than 0. The work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path along the radial direction from infinity to the point B. At some intermediate point P, at a distance x from source charge, on the path, the electrostatic force on the positive test charge is equal to product of Q naught and E. To prevent this acceleration, equal and opposite force, that is minus Q naught E, has to be applied on the test charge. Work done to move Q naught from P to Q through dx against Q naught E is dw equal to dot product of Q naught E vector and dx vector. Total work done to move Q naught from infinity to B can be obtained by integrating dw with the limits infinity to R. Dividing this work done by positive test charge, we get the expression for potential at that point, which is equal to 1 by 4 pi epsilon naught into Q by R. Clearly, potential due to point charge is inversely proportional to distance of observation point from the source charge. As discussed earlier, potential due to point charge is inversely proportional to distance of observation point from the source charge. Whereas, as studied earlier, electric field due to point charge is inversely proportional to distance of observation point from the source charge. Figure shows the variation of electric field and potential due to point charge with distance. Expression for potential due to point charge is true for any sign of source charge. Hence, for positive source charge, potential is positive and vice versa. The variation of potential due to point charge with distance from it is represented in the image. The graph for positive charge is in first quadrant, whereas for negative charge is in fourth quadrant. Principle of superposition of electric potential states that electric potential at a point due to a charge is not affected by the presence of other charges. And since potential is a scalar quantity, therefore the potential at any point due to group of point charges is found by calculating the potential due to each charge, as if the other charges were not present, and then adding algebraically the quantities so obtained. As we learned in the last chapter, an electric dipole consists of two charges q and minus q separated by a distance 2a. Its total charge is 0. It is characterized by a dipole moment vector p vector whose magnitude is product of q and 2a and which points in the direction from negative q to positive q. As before, we take the origin at the center of the dipole. Applying superposition principle, the potential due to the dipole is the sum of potentials due to the charges positive q and negative q, that is equal to q by 4 pi epsilon naught multiplied by q by r1 minus q by r2. Where r1 and r2 are the distances of the point P from positive q and negative q, respectively. Using cos law we get r1 square equal to r square plus a square minus 2 a cos theta, where theta is angle between P vector and r vector. For short dipole, we take r much greater than a and retain terms only up to the first order in a by r. On solving we get r1 square equals to r square multiplied by 1 minus 2 a cos theta by r. Similarly, r2 square equals to r square multiplied by 1 plus 2 a cos theta by r. Using the binomial theorem and retaining terms up to the first order in a by r, we obtain 1 by r1 approximately equal to 1 by r into 1 plus a cos theta by r, and 1 by r2 approximately equal to 1 by r into 1 minus a cos theta by r. Putting value of 1 by r1 and 1 by r2 and using p equal to 2qa, we get potential due to dipole equals to p cos theta divided by 4 pi epsilon naught r square. Expression for potential is, as indicated, approximately true only for distances large compared to the size of the dipole. For a point dipole P at the origin, the expression is, however, exact. On the dipole axis, theta is equal to 0 or pi and is given by positive sign for theta is equal to 0, negative sign for theta is equal to pi. The potential in the equatorial plane, where theta is equal to pi by 2, is 0. The important contrasting features of electric potential of a dipole from that due to a single charge are firstly, the potential due to a dipole depends not just on r but also on the angle between the position vector r and the dipole moment vector p. It is, however, axially symmetric about p, that is, if you rotate the position vector r about p, keeping theta fixed, the points corresponding to p on the cone so generated will have the same potential as at p. Second, the electric dipole potential falls off, at large distance, as 1 by r square, not as 1 by r, characteristic of the potential due to a single charge. You can refer to the previous graph of 1 by r square versus r and 1 by r versus r, drawn there in another context. An equipotential surface is a surface with a constant value of potential at all points on the surface. That is, there is no potential difference between any two points on the surface and no work is required to move a test charge on the surface. Further, the electric field at every point is normal to the equipotential surface passing through that point. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit test charge against the direction of the component of the field, work would have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any two points on the surface and no work is required to move a test charge on the surface. Also, equipotential surfaces can never intersect each other. If they do so, then normal to them, that is, electric field lines will also intersect. That is not possible, as discussed in previous chapter. The degree of closeness of equipotential surfaces represents relative strength of electric field in that region. Hence, equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around a charge configuration. For a single point charge, potential is same at equal distance. Thus, equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Now the electric field lines for a single charge q are radial lines starting from or ending at the charge, depending on whether q is positive or negative. Clearly, the electric field at every point is normal to the equipotential surface passing through that point. For a uniform electric field, say, along the x-axis, the equipotential surfaces are planes normal to the x-axis, that is, planes parallel to the yz plane as shown in figure. Equipotential surfaces for a dipole and two identical positive charges are also shown in the figure.